Morning, everybody. I just realized today that we're very well ahead on our schedule, so I am thinking of cancelling tomorrow's lecture because we're already getting on to threshold problems today. All right, let's have a look at what we did yesterday. Well, yesterday we learned how to add heat exchangers, how to design a heat exchange network, a new heat exchange network that meets maximum energy reduction. So that is pretty much the first step that we'll be talking about over here. Perform an MER design for a certain number of units. So that is where you're putting in extra units because you need to do looping, as we did yesterday, where we changed that 400 kilowatt heat exchange, 480 kilowatt heat exchanger to a 400 kilowatt heat exchanger, and also the 500 kilowatt heat exchanger we reduced to a 200 kilowatt heat exchanger to prevent delta T min violations. So we're putting in extra heat exchangers when we do this. Perform an MER design for UX units. UHEX units. So UHEX is more than the minimum necessary. Try to ensure that the design meets human MER separately above and below the pinch. So that is when you use one utility. Below and above this pinch, you've only got one utility. And you try and achieve that, but sometimes it is not possible. So on the hot side of yesterday's example, we could meet human MER. Okay. Step 2, compute the minimum number of units. So there we use the number of streams plus the number of utilities minus 1, and we can see how many independent heat loops there are. And these heat loops can be eliminated to reduce the actual number of heat exchangers. So by doing that calculation, you know how many units there are already in the design, and how much is the minimum. And when you subtract the two, you get the number of independent heat loops, and that's the number of heat exchangers you can eliminate. But when you eliminate those, you tend to, for each loop, eliminate, but it may cause, and it usually does cause, a delta T min violation. So you identify the heat path and perform energy relaxation. The heat path is one that goes through by increasing the duties of the cooler and the heater on the heat path. So you choose a heat path that goes through both a hot utility and a cold utility, and then you can increase the delta T min. Okay, now what I didn't show you yesterday, well, on Thursday when we last had this thing, is when we go back to this, go back to a previous one. Right. So where's our delta T min violation here? 123. We fixed that one. Oh, we're about to. Let's go back. Let's go to fixing this delta T min violation. This one we have corrected. Let's go back there. Right. So there's 110 degrees. There's 113 degrees. Cold is hotter than the hot, and we need to adjust that by 23 degrees. Now, we can take this heat path as shown. So it does go through a hot utility and it does go through a cold utility. But we could have also chosen this heat path. There's the hot utility. It could have gone through here let me get a pointer and pen color. Right, we could have done this just as easily. And that's absolutely valid. As soon as we add enthalpy onto this hot heat exchanger, the hot utility, we're going to subtract energy over here. So we add energy here, which means that these temperatures would get less, and that's exactly what you want. You want this cold temperature to get less. You want it to go down to 100 degrees C. So 13, let me get out my calculator and quickly do the calculation. 13 degrees. Just get to the calculator. Right. 13 degrees, 13.33 degrees, and the CP of that stream is 3. So we multiply by 3 times 3 equals, X is going to be 40. We will have to add 40 kilowatts of energy to get this stream down to 100 degrees C, so that we don't violate the delta T min. So compare that to the loop that we've chosen over here, where instead of changing this step, let me go back to the proper pointer. Instead of changing this temperature, 113 degrees, we rather change this one. Then this one must increase to 126 degrees C. So that is plus 13. It's the same temperature, of course, 13 degrees, 13.33 degrees, and you multiply it by the CP of 2 times 2, and that gives us 26 kilowatts. So that's that answer there. 26 kilowatt X equals 26 kilowatts if you go through this thing. And the reason is it's still the same amount of degrees of temperature that you must change, but the CP is lower, and therefore you need less energy. So this is a really important point when you're choosing the loop that you go through. Noticing that you can either change this temperature with a CP of 2, or you can change this temperature, which has got a CP of 3. And of course, you're going to choose the stream where the CP is the lowest. Okay, so that's a really important point that you're going to have to use when you do Thursday stat. In choosing the line, of course, it's only on these horizontal lines that the temperatures will change. So that temperature is going to change. If you're looking at the red loop, that temperature will change. That temperature will change. That one, and that one. Doing the red loop. If you go through the black loop, that temperature will change. That temperature will change. Go to the next horizontal line, that temperature is going to change, and then that temperature will change, and that temperature will change. Okay, so that's the principle. Choose a loop when you do the relaxation part. This is the relaxation, energy relaxation. That is called energy relaxation. When you do energy relaxation, don't choose the red loop, choose the loop that goes through the smallest CP of 2, where you want to change the temperature. If you go straight up here, the horizontal line is where the temperature changes. That's the one you want to change. Okay. Now we can go on to finishing, summarizing what we did in these lectures. Right, so For each loop, eliminate a unit. If this causes a delta Tman violation, identify a heat path and perform energy relaxation by increasing the duties of the cooler and heater on the heat path. And that way you're going to get, let's say that there are 3 independent heat loops. That means you can eliminate 3 exchanges. You will have 3 different scenarios, 3 different designs. And the fewer heat exchangers you have, the less the capital costs, but the higher the running cost, because as you eliminate heat exchangers, you're reducing the capital cost, but you are using more steam. You're using more hot utility, which is the expensive one, and that will increase the running costs. So essentially, you can do those 3 designs. If there are 3 independent heat loops, you can do those 3 designs and check which is going to be economically the most beneficial. Loops improve energy recovery. Loops is what we were doing yesterday in the example, the last part of yesterday's lecture. They improve energy recovery and heat load flexibility at the cost of extra added units. So we get improved energy recovery, so we don't use as much hot utility, but it's at capital cost, because we're using more heat exchangers. Okay, so that covers removing heat exchangers from a heat exchange network, and that's what we're going to be doing on Thursday in the TUT. Yes, Philip.
Prof, just before we move on, I'm still not sure when we would prefer doing the loop breaking versus like splitting the loops and adding 2 heat exchangers. From what I understand, splitting the loops will allow us to actually reach the minimum amount of heat exchangers. But I understand that it's not as good because you have to then remix streams and can complicate control. But how do we prefer the one above the other?
Okay, so at one stage when we were doing that splitting of streams, it said don't split unless necessary. So that always holds. You will not split unless it is absolutely necessary. So once it meets those constraints where it says now you've got to split, we went through those constraints, which are quite complicated. You've got to look at 2 different constraints. One about splitting cold streams, and one about splitting hot streams on each side of the pinch. Only if those constraints say that you have to split a stream, will you split a stream? Okay, so I have in the past with exams just say don't split streams unless necessary. I actually put it in, but it's not necessary for me to put it into the exam question. You should never split streams unless it's necessary. Okay, so it's always going to be better to rather do a loop design rather than a split stream design, if it's possible to do a loop design.
Yes. Okay, no, thank you. That makes sense.
Okay. Right, so let's have a look at this. Threshold problems. So networks with excess heat supply or heat demand may have MER targets with only one utility. So in other words, you might not need to have steam, or you might not need to have cooling. Such designs are not separated at the pinch, and they are called threshold problems. So if we consider this problem, 2 hot streams, 300 to 200, 300 to 250, and this cold stream, which you can see 200 to 30, you've got plenty of temperature difference because the coldest of these streams is 200 degrees. So you got plenty of temperature difference over here. And even this one, 200, is the same as the coldest of the hot. So so this is going to be a very easy heat exchanger to match this C1 with these two. Let's just have a look at the kilowatts. If we've got 100, this will be 150 kilowatts. This one is 50 degrees times 2 is 100 kilowatts. So we've got 250 kilowatts of hot stream of energy in the hot streams. And here's 1.2 times 170, which is probably around 200. 150. All right, so the duties are the same, but there seems to be more hot utility than cold utility. There seems to be more hot enthalpy in the hot streams than in the cold stream. Well, I've got my calculator available. Let's quickly work it out. 170 degrees for the cold stream times 1.2. Yeah, I was right, 204. So we've got 204 kilowatts in this that must be added to the stream, and we need to take away 250 from these two. This one is 100, this one's 150 kilowatts. Okay, so now we're going to do something rather strange. Okay, assuming, oh, there we go, assuming a value of delta T min equals 10 degrees C, which is a normal thing. The problem table, well, this is the enthalpy cascade that they do in our textbook, but it's the same thing as the problem table. You first assume that you don't need any steam, then you go through all the different temperatures with 10 degrees less than the, remember the H1 started at 300 degrees C, so this is 10 degrees less, and we go through all of the temperatures, and these are the numbers we get. We start at 0, and we look at these numbers, and it says that we need 46 kilowatts of cooling water, and we need no steam at this stage. But then you go and have a look at which is the smallest number over here, and none of these numbers is negative, because you have to look for the smallest number and then make it equal to 0. So obviously this is a pinch problem because it doesn't require steam. It only requires 46 kilowatts of cooling water. Okay. So that shows that it is a threshold problem. If you had it the other way around, that there was more enthalpy in the needed for the cold streams to heat up. Google Chrome. Okay. I don't think it's somebody asking. Wait, I'm not even on the comments. Let's go to the comments. Okay. So that is the one option when there's more enthalpy in the hot streams than in the cold streams. Then you need some extra cold utility. You need cold utility, but you don't need hot utility. That's the one type of threshold problems. The other one is you start at 0 and you end up with the smallest number down at the bottom here. So let's say you end up here at minus 70 at the bottom here. Then you would choose 70 as your steam, the amount of steam that you need, and redo this thing and land up with 0 at the bottom. And that's another threshold problem, because you need no cooling water. When you get down to the bottom, the amount of cooling water is 0, and the amount of steam is 70. Okay, so let's carry on with this particular problem. This is not moving on. Right, now we say, let's assume a value of 105 degrees C as delta T min. If delta T min equals 105 degrees C, then we get this sort of enthalpy cascade. That's 300 becomes 200, right? should be 205 or 195 or something. Yeah, that should have been 195. Oh, there's the 195. So that's the cold. Oh, that's one of the cold temp. That's the cold stream temperature. It's now hotter than the hot stream temperature, because now we've subtracted. Remember, the one hot stream started at 300 degrees C. We've subtracted 105. So one of the temperatures is 195. Cold streams remain the same, and that's still 200 degrees C. So this is the first temperature we've got here is the temperature on a cold stream, and then we've got the hot stream and all the rest of the streams. Cold stream's lowest temperature was 30 degrees C. And that's the lowest one on this thing. So when we do that, we do get a negative number in the enthalpy cascade. And that is the -6 over there. So we put 6 kilowatts of steam required, and then we get an ordinary pinch problem. So there's 6, etc., and we get to 52. And if we take 52 minus 6, we still get 46. As you will always do, the difference between the enthalpies of the hot streams and the enthalpies of the cold streams is always going to be the same, even if you use hot utility. Okay, so this is madness, you know. Who's going to use a delta T min of 105 degrees C? But it was to show that if you make the delta T min high enough in a threshold problem, you can get to an ordinary pinch problem. Okay. What that means is at a certain threshold temperature. So looking at our problem at 100 degrees C, that is where you start getting pinch problems. When the delta T min equals 100 degrees C, here's delta T min on the x-axis. And when we made it 105 degrees C, we needed 6 kilowatts of steam. And instead of 48 down there, we needed 54. Yeah, 54 kilowatts up there. And if we made the delta T min 150 degrees C, we would need that much steam and we would need that much cooling water. But the difference between the steam and the cooling water is always 46. So the difference, if you take delta T min as 150, you'd still get the difference between that point and that point as 46 kilowatts. Okay. Now, as soon as you have your delta T min less than 100, you will still need your, like we did it for 10 degrees C, somewhere around here. And at 10 degrees C, we still needed the 48 kilowatts of cooling water. And it doesn't matter how low you've made your delta T min, the numbers still stay the same. You need zero steam, and you need 48 kilowatts of cooling water. So that's the nature of threshold problems. So, I mean, at reasonable delta T mins, reasonable delta T mins are at these sort of temperatures. So, threshold problems do not have a pinch and have non-zero utilities only at one end. That is the property of threshold problems. So you can see that if you want to maximize your delta T, it's useful to know what the delta T min, the threshold delta T min is. And so how do we know what that number is? And so that's an interesting problem to have to calculate, and I'm sure we're going to do a touch of that nature. Okay, let's have a look at this, the hot and cold composite temperatures, and what we find here is that All right, this is 100. This is 14 degrees C across there. So let's assume that we've got a 10 degree delta T min equals 10 degrees C, and you've got this hot composite curve, and you've got this cold composite curve starting over here and going up till there. So if you move this cold composite curve horizontally, you can move it even further left, and eventually you're going to land up, if it lies over here. Let me maybe get a pen and ink color blue, and let's just draw it in over here somewhere. Nice straight line. That's an arrow. Okay. Then we might get our 10 degrees C temperature difference from there to there. But now that's silly, because we're going to have to use cooling water to cool down this very hot stream over there. And we'll still use the same amount of cooling water, because now we need cooling water to cool down the coldest part of that hot stream over there. And then the heat exchanger between these two, the cold and the hot stream, the process heat exchanger, it's got a lower temperature difference, log mean temperature difference for the exchanging of the process streams, than if you used delta T equals 14. So you'd want to push the DT min to its maximum. Yeah, exactly, to reduce the heat exchange area. That's precisely it. So there's no sense in taking this point any further than underneath the hottest part. So once you can move this blue line left from, let's say from over here somewhere, you move it left in this direction until this point is directly underneath that one, and then there's no sense in going further, because now you've got that much cooling water and you don't need any steam, because steam, if you got it over here where I've drawn it, let me get back to the pointer. If you've put your cold stream at this point, you're going to have steam. You're going to have this much steam from there through to there. That's now you're going to need steam. And then you're going to need a lot more cooling water, because you'll need cooling water from the bottom of this arrow right through to there. So you need more steam and more cooling water. But as you're moving this arrow to the left, eventually you're going to need no steam, and then there's no more sense in going any further to the left. That's how much cooling water you use. And that is that point there. You move it to the left until, if you move it to the right any further, then you start having to use steam. There we have to use steam. And so we've moved it even further to the right, and we're sitting at that point, and that's silly. You move it down until there, and it's no point in moving it any further to the left. So that is the answer. That is where we want to be. So increasing the driving forces, this 14 degrees C, any further than 14 degrees C by moving it to this point here, beyond the threshold value, leads to additional utility requirements, and then we start going up these curves over here. We start needing steam, and that's just not, it doesn't make sense. Right, so that's the threshold problem. Now, so hide ink markup. That wasn't it. Okay. All right. So this is what I was illustrating. As we move it to the left, we can get down to 10 degrees C there. And then we need cooling water over there, and we need cooling water over there. But the sum of these two thick blue lines remains this value here on the y-axis. You still need the same amount of cooling water. It's just that this heat exchanger would have a very high delta T, and this one would have a lower delta T. So anything less than 14 degrees, you still need the same amount of cooling water and 0 steam. That is where we want to be. If we push it to the right, as I was saying, we can have 20 degrees C from there to there. That's delta T min. But now we have to use steam to heat up this cold stream. Its last little bit. We have to use steam for pushing that up, and the cooling water has got higher, and that's what's happening on this graph. So, design guidelines. As soon as you see you've got a threshold problem, establish what is that threshold delta T min. What is the value? In this last example, it was 14 degrees, but you need to recognize what that delta T min is. Common practices for delta T min are process 10 degrees C, so that's what we've typically been using. As soon as you've got refrigeration, then you want to keep it very low because of the cost of refrigeration. And when you've got a boiler, you've got air heat transfer, and therefore you need a bigger delta T min. So that is just delta T min from experience. Compare the threshold delta T min, that one that you've established up there, to the delta T min experience, and classify as one of the following. The pinched problem, you actually do want a high delta T min. So high delta T min, remember delta T min is on the x-axis, so we push it high enough that we can that we've got at least this thing that we're talking about in experience. And then it's a normal pinch problem because we are using both steam and cooling water. So it's a pinch problem, treat as a normal pinched problem. Right. Or else it's a threshold problem. If whatever the delta T min from experience is, and it's less than that delta T min threshold, which is that point. If it's less than that, then it's a threshold problem, and you must satisfy the target temperatures at the no utility end. So in other words, then you will use delta T min as the threshold delta T min, because it's no sense going further along this line. You're simply decreasing your delta T in the heat exchangers. So you might as well use delta T min threshold, because there's no penalty in using more steam or anything like that. Okay. Okay, so the graph shows the effect of delta T min on the required levels for a process consisting of 3 hot and 4 cold streams. Okay, so there are the 4 cold streams. So this is delta T min. As soon as it goes above 50 degrees, then you start using cold utility. It's not quite drawn quite right, because these are always the difference between these two is always the same when you pull it down. Okay, so this is how much hot utility you require at below the threshold temperature, 217.5 kilowatts, BTUs per hour, let's call it kilowatts for convenience. So now design a network for UMIN and MER for the process. Identify 2 essential matches by satisfying target temperatures at the no utility end. Okay. Delta T. So we know that MER is the delta, the QH min equals 217, and we're not going to use cooling water. We can do that by adding up all the enthalpies of the hot streams and adding up all the enthalpies of the cold streams, and there'll be more enthalpy in the cold streams. You need to push more heat into the cold streams to heat them up than you need to remove from the hot streams. Okay. So knowing that your essentially your pinch is where we have where we're going to need hot utility over here on the cold stream. So essentially that says that the pinch is going to be on the right hand side, because you only use hot utility on the hot side of a pinch. So there we saw that it needs hot utility, and so we put the hot utility. The hot utility is going to occur over there. That means the pinch, because it's a threshold problem, the pinch is either on the left or the right. And in this case, it's going to be on the right-hand side over here. Okay, so let's have a look at CP. CP hot must be less than CP cold. So we choose this match, must be less than CP cold, 1.3 with 1.6. And that is 100, that is 50 degrees C difference on this side, and it's more than 50 degrees C difference on the other side. If you make that 505.6 kilowatts, then you have finished H3. Okay, the next one you do, you can do against the pinch will be this heat exchanger where CP hot is less than CP cold. And if you use 341 kilowatts, then you sort out this C4 totally. Now you've only got two cold streams left, that one and that one. And you've got three hot streams because this hot stream is not complete yet. So you've still got three hot streams. Okay. Oh, wrong way. Okay. There we go. So the next one is against the pinch. CP hot. Now we're going to go for the biggest CP of the cold streams, because remember, CP hot must be less than CP cold. So this is the third heat exchanger, and we've chosen these matches so that every time we have the CP hot is greater than the CP cold, we would not be able to match this CP with any of these two. Yeah, those we would not have been able to match with this stream. So with that stream, 2.3 and 4, no problem. 300 degrees and 400 degrees, that's 100 degrees C difference on this side, and it's going to get bigger on the other side. So that is 570, so it's 170 degrees on the other side of the heat exchanger. And now we've also sorted out this cold stream. Okay, now the only two hot streams that remain, there's only one, there's two cold streams, these two, C1 and C2, but now we're well away from the pinch, and now we can exchange with these hot streams with this cold stream over here. That didn't really matter which one you use, that both of these cold streams are 1.6. So there's 200. See, now this temperature of this hot stream ended at 200, but because we put in this heat exchanger over here, it's gone up to 416. And therefore, there's not a problem with this 300 degrees over there. This is already 116 degrees hotter. Oh, sorry, we're looking at the wrong one. 200 degrees. If we try to match these two, I'm looking at this heat exchanger now. If we try to match that up against the pinch here, we would have 200 degrees on both sides. But now this one has already been heated to 416, so we can match it with the 200 quite easily, even if we have even if we had the wrong CP match. But in fact, the CP match is still fine over here, no problem. So we can use kilowatts that sorts out the H2 thing. We can't match H2 and C2 due to, yeah, you see this C2 we've already heated up. That's right. I did say we could have chosen either one of these based on the CPs, but this one's already heated up to 416 degrees. That one's 416.3 degrees, so there's 0.3. There's only the delta T of 0.3, and at least the hot is hotter than the cold in this case. But yes, that's quite correct. Thanks, Yuri. So, so this would have been the only match from H2 416. We can match with the 200, and well, we don't see the temperature over here, but that is a nice high temperature over there, so we can match there and make sure that we finish off the enthalpy of this stream is 412.8 plus 38, because we needed those two heat exchangers. And once we take off that 38, then we've sorted out H1 as well. Okay, so then by putting in these two heat exchangers, we've sorted out H2 and we sorted out H1. So all of the hot streams have been sorted out. And once that is done, then the only thing left is to fix the cold streams by adding the amount of heat that's required. Okay, so it's a complicated heat exchange network, this one, but the point over here, as this is a class exercise, is that by knowing that it's a threshold problem, you knew where you can figure out which side the pinch goes. So if you need hot utility, the pinch is going to be on the right-hand side, fully on the right-hand side. And if you needed cold utility and not hot utility, then the pinch would have been completely on the hot side here, on the left-hand side. Okay, so that is pretty much all right. Note, U-min equals number of streams plus number of utilities minus 1. There's one utility. We know that because it's a threshold problem. So U-min equals the number of streams, and there are 7 streams. Let's count these heat exchangers: 1, 2, 3, 4, 5, 6, 7. So we actually are at U-min on this problem, because there's 7 streams and U-min equals 7. And we're staring at a blank screen. So that is the end of that lecture. Right. Thursday's TUT will only be on the removal of heat exchangers to achieve U-min. That's correct. Yeah. By the way, when I ask a question like that, where I ask you to remove heat exchangers, I will rather give you the heat exchangers. Remove the 412 kilowatt heat exchanger when I ask a question like that. So it's not necessary to, if I do that, then you don't have to go and work out U min and how many independent heat loops there are or anything like that, because I'm asking you to simply remove one heat exchanger. And I'm specifying that heat exchanger so that you don't have to go and randomly choose a heat exchanger that you want to remove. I will say, let's remove that heat exchanger, and then I want you to determine how much extra energy we're going to require when you remove that heat exchanger. So it's not this work. That's why I'm feeling a little bit uncomfortable that we've done threshold problems already, when Thursday's TUT is going to be on removing heat exchangers. So, in fact, no, 4th years working on a third quarter. You're on quarter number 3 at the moment. It means you don't have the test week. And I always arrange the design review during the test week. So the test week is next week. Okay. You see, that's the problem. Then there are no lectures during the test week. But we can arrange to have lectures in the test week. But that's the reason that I arranged the design review on the test week, is so that you're not going to be have a clash with one of your lectures, because during test week you should have no lectures, of your third quarter subjects. So yeah, next week there should be no lectures for you as 4th years, but you will have your design review on the Thursday and Friday, as far as I remember. It should work out that way, if next week is the test week. Okay, so before we end, I must just decide. No, there's still a bit more, Francis, and that is grand composite curves. With grand composite curves, you can work out quite interesting things about the utilities that you require and the temperature of utilities that you require. But that's the last part. That's the last bit of work, and we've still got 2 weeks of lectures after the test week, so that's plenty. Right, so I'm going to cancel both of these lectures. So the next time I see you is the TUT on Thursday, which will be a TUT test, this continuing assessment type of thing, and that is going to be to remove heat exchangers from a heat exchange network. Okay, and then after test week we can start working on grand composite curves, and that's the end of the semester. Okay, guys, I'll see you at design review. Oh, I'll probably see you tomorrow at CPJ as well. Okay, stop recording. I believe I didn't stop the recording yesterday. Oh no, I stopped. Oh, I see. I stopped the showing on the slide, and I